All right, let's just get started. I'd just like to say welcome to you, Dan. It's a pleasure having you do this live online pre-seminar to our actual event taking place on the 18th to 19th of November this year in Copenhagen. So yeah, take it away, and thank you very much.
You're very welcome. I want to thank you very much and say I'm very excited and honored to be part of your seminar series. We're really all on a mission to try to help improve the outcomes in people's designs. And I want to start with this. Basically, this is my foundation presentation that I use now. It's wasn't where it started, but this is where it's come to. I learned more and more about signal integrity and PC board design, working with people like Happy and with Rick Hartley and originally Ralph Morrison, to try to understand how things work and what it takes to be able to create a design that works properly. So this is where this comes from, and I'll explain what this whole thing about the billion-dollar mistake is. Um, I'm assuming that the audience are either electrical engineers or PC board designers, and so my first question is to ask you to think about how many times do you have to respin the board in order to become functional for sure, but to become compliant. And that's what's become an issue as the technologies continue to change and the products are faster and smaller, and compliance requirements are more severe, that failing to understand electronics from an energy perspective is going to continue to lead you down a path of failure. So my disclaimer is I'm a broken record. If you've ever taken any of my classes before, you're going to hear the same thing over and over again, because it's all about dielectrics, and that's what we have to start focusing on. So wanted to specifically concentrate on creating waveguides, transmission lines, because the energy that we care about is moving in the dielectric. And that's what the problem has been. We were taught to think about energy directly related to the wires themselves. And that perspective is what has led us to make very bad choices in the way we design things. I want to apologize to anybody who's really an electromagnetic field physicist, because I'm going to simplify things down to the level that I can understand them, because most of my efforts when I was studying with Ralph Morrison was to convert his high-level physics and math into words that normal people could understand and apply to their day-to-day life. But one thing that Ralph said in every one of his lectures, he would start and end with this very profound statement: buildings have walls and halls, people travel in the halls, not the walls. Circuits have traces and spaces. Energy and signals travel in the spaces, not the traces. He said this over and over and over again. He wrote his first book in 1967 called Grounding and Shielding Techniques. Most everybody who wants to pretend they're a signal integrity specialist has at least one copy of the 10 versions of that book that he published through Wiley. His last book was Fast Circuit Boards Energy Management. He wrote 2 books after I dragged him out of retirement when I first met him and got him back involved in the industry. But this statement never really hit me as how important it was until I was writing his eulogy, which was the wrong time for me to finally get it. But he was telling us all along that we needed to focus on the dielectric and to manage the places where we wanted the energy to go, and control that using the walls to control where people go, or the traces or the planes to control where the energy moves. So I wrote this song, and unfortunately can't hear it. That's my daughter Gabrielle playing the guitar and singing for me. But wanted to find some type of a way to help people to reconfigure their brains. So I figured the best way was to create an earworm And this is sung to the tune of Meghan Trainor's All About That Bass. So it's because it's all about the space, And so there's a YouTube link there that you can see. I think we'll present. I'm sure that Azitech will provide the PDFs for this presentation. So here's what's going on. We're all facing harder job to do. The IC companies are building chips with smaller and smaller transistors. We're into I think they're working on sub-nanometer geometries in some of the newer fabs. These transistors switch in terahertz. So the energy management and signal integrity challenges are only becoming more and more difficult. I'm working on a project for terabit Ethernet. There are signals in buses that switch in 4 to 10 picoseconds. So we have to really understand energy for signal integrity and energy for delivery related to EMC. At the same time, we're creating these ICs that are switching faster and much easier to disturb. We're subjecting them to environments where we expect them to be more robust and resistant to interference and to reduce the amount of energy that they're radiating and causing difficulties with other surrounding systems. So this whole thing is going in two different directions. We're making things that are noisier and weaker, and the industry expects them to be stronger and quieter. And then they extended the band into the upper and lower regions so that the compliance bands are even harder and wider than they ever were before. So the plan has been for people to design systems, test them, and hope. And when it doesn't work, they look at it, wave their hands, look at one thing to change, and try again. And the status quo, basically, from the industry that I support and what I hear from other signal integrity specialists, is this 3 to 5 cycles. And this cost isn't in the budget. The time isn't in the budget. And all of this directly affects the bottom line, so that your customers don't get product when they want it. You miss market windows. Companies go out of business every month because they can't afford to do this, or they can't make a product quick enough in order to meet a marketing window. So everybody loses because we don't have the right perspective in what we design. And their impact is, instead of working on their new project, they spend a lot of time trying to fix the old one, and billions of dollars are lost each year designing things that are most likely not going to work. And as I started to ponder this perspective, I was like, why in the heck are we doing this? What caused this iterative negative cycle that we continue to be in? And what I went back to is my training and what my mentors in my early career had taught me. What I learned in school is this drawing. And this drawing is something that everybody loves and understands, they think. And this is where things go very, very wrong. The whole idea is that we see a battery on one side and we have a load on the other side and a switch. And then they put these arrows that are supposed to show the movement of energy in this design. So the idea is that the arrow shows the flow of energy, and it suggests very strongly that the energy is in the wires. So, but this perspective was fine for a long time, because the geometries of the ICs that we used were so large relative to the structures that they were used in, that everything was lumped. So you could do stupid things and it would work. So we created a whole network and system of design guidelines and perspectives that wasn't based on what was the right thing to do, but it was based on what didn't make it broken. So we have these rules that were misguided from the very beginning. And this is, this is the industry. This is myself, my peers, the people before me, except for Ralph, who just didn't focus on the science of electromagnetic energy. So we have the wires. The arrows show the current flow. The idea then is we decided to call the wires the conductors, because they are conducting the flow of electrons in the electronic circuits. And then it goes in a loop. It goes from plus to minus through the circuit. The loop now becomes a circuit. So these words that we use are misapplied to the actual function. And this is what sets up all of the bad design guidelines that people are using. So if this was true, as soon as the switch is closed, the energy would be instantly seen at the load, and there wouldn't be such a thing as a signal integrity or EMC problems. But at the same time, that means there wouldn't be no such thing as radio, because it's the same energy. For some reason in electronics, we would take the energy, the electromagnetic field, the radio waves that we fully believe travel in space. And when we put it on a printed circuit board, it magically turns into electrons and wires, and all reality starts to go away. And so all of our design guidelines are just wiring things up with no consideration for the movement of energy, which occurs in the dielectric or the space between the wires. And the last thing I want to say is that there wouldn't be any life on Earth because the light from the sun doesn't get here by wires. There's no wires connecting us to the sun. So this every day in our face proof that our perspective is wrong continues to be ignored by the industry. And this is the mission that I'm on, because Ralph Morrison set me on that mission. And that's the mission that Azitech and their training and other good signal integrity people are trying to get the industry to refocus on the dielectric and the energy that it's traveling in that space. So the wires aren't the conductors. They form the boundaries, just like the banks of a stream, forming waveguides. The energy doesn't flow through the wires, it travels in the space between the wires. This space, or the dielectric in a PCB, is the actual conductor. The energy is carried by a moving electromagnetic fields in the dielectric, not electrons flowing in the wires. And the whole idea of current flow, an ampere is a coulomb of charge moving past a point in the dielectric in a second. So it's moving through the space like gallons per minute in a hose. Very, very similar. But you have to think about the idea of the energy moving in the dielectric. So Ralph spent a lot of time with me on language. And whenever I would say the wrong word in the wrong context, it would mean, a half hour to an hour lecture on how that was the wrong thing to say and what the right thing to say. So these improperly connected words, the circuit and current and conductor, allow us to ignore the facts that the science has always been about. So you have to start thinking about these words in their proper context. The conductor is actually the dielectric, and the energy moves in that dielectric, and there is no return current. Energy goes from where it is to where it has to go based on the transmission line that connects the places together. So again, when we were back in the TTL days, it didn't matter because the switching speeds were so slow that everything was lumped. So there was plenty of time for the energy to settle down between events. There weren't reflections, there weren't signal integrity problems, there were only rarely EMC issues. And the problem is that as the industry gradually changed the technology of the devices, we went to smaller geometries. You would change a chip here or a chip there. And then we started to see increased failures in EMC. And we didn't think anything about it. We just accepted that and tried to do what we could in order to figure out what was wrong. I spent many, many hours in the mid 80s and 90s sitting next to my customers in the test chamber, trying to figure out which wire to move or what circuit to change in order to pass EMC with absolutely no idea of what was really going on. We never understood the fundamental issues. We used band-aids like ferrites and inductors and just totally ignored what was really going on. And we would find something that worked on one board and think, wow, we're great, we figured this out. But when you try to do that same thing on another circuit board with the same problem, it didn't fix it because it wasn't a fundamental issue. It was just a band-aid that corrected one piece of the puzzle. And what I want to do in this training that I'm going to do in November is to create the foundation at which you can build a board and not only know that it's going to work, but if you have existing issues that you'll be able to understand what it is that's causing those problems and be able to change the foundation of that problem. And it's like I said, it's just like the frog. If you put a frog in a boiling pot of water, it's going to jump out. But if you put it in a cold pot of water and slowly heat it, it's going to let itself be cooked. We've let ourselves be cooked, and nobody seems to care. It hasn't changed what's being taught in schools. They still focus on circuit theory and electrons and wires. They make the idea of electromagnetic field physics, it's evil, hard math. People will go through those classes as quickly as they can and forget it as quickly as they can. They do not tie the ideas of electromagnetic field behavior to the design and manufacturing of electromagnetic systems, which is what's the big problem. There is no impetus for the academics to change what they're doing because their customers, the big electrical engineering development companies like General Motors, General Electric, Ford, Airbus, they aren't going back to the universities and say, change what you're teaching. We need a different skill set. So as long as nobody tells them they need to change what they're doing, they're not going to. There's no financial reason for that. And the other piece of inertia is that the textbooks that are being used were written by the tenured professors. And if there's going to be a change in curriculum, they won't be the ones that are writing the textbooks. So they don't want to let that happen either because they don't want to lose that revenue stream. So there's all this inertia that keeps creating a technical skill set that isn't adequate and doesn't address the actual requirements to do good PC board design or electronic systems design. And the result is continued poor designs that fail EMC. So this is something we have to start to think about. We are involved with developing products that generate, control, and consume electromagnetic field energy. We were taught this about electrical energy being made up of electrons moving in the conductors. You turn on a switch and the current starts to flow in a loop. The wires carry the energy and the load sees the energy instantly. That's not what happens. There is no loop. There is no return current. The energy goes from where it is to where it has to go. When you turn on a switch, it adds a new space, just like turning on a water faucet. The water starts to flow into the hose, finally makes it to the other end of the hose and comes out of the energy. So this is the idea of current flow, is the energy that's moving in the dielectric. So it wasn't what we were taught. And the problem is that the results are that we have issues with both signal integrity and EMC. And that's what we want to change. These things I'm talking about and what I'm going to teach in November are what I used every day in the designs that I'm responsible for. What I use to help my customers to become successful, because I work in automotive. I do very high performance electronic design, everything from network servers to electric vehicle inverters. And applying these perspectives and the principles as achieve means success. Every design that I design always works the first time. When my customers listen to me, their designs work there after they respin them. If we start from the very beginning and do a full design cycle together, first time compliance is what we achieve. And that's what has to be the goal. Not we hope it's going to pass. It's we design this system. We know that it's going to work because we followed the rules. And that's what we're going to talk about in these classes, is what are the underlying very simple rules that you need to understand. This is what I extracted from my years of study with Ralph Morrison. And these are the foundation of your future. So it's all threes. It's really wonderful because three is an easy number. To contain field energy, you only need three separate components. You need two discrete conductors, what I'm calling the wires, or and the dielectric or space. The energy then is stored in the space between the two wires. There are only three components in the universe that you can use to do things with the field. You get the conductors, you get the spaces, and you get a switch. There's nothing else. The most complicated microcontroller or microprocessor is a giant switch array. And these switches turn on and off and let energy go or not go from one space to the next. That's all there is. And then you can only do three things with field. You can store it, you can move it, or you can convert it to kinetic energy. You can turn a motor. You can vibrate the filament of a light bulb and create light. You can send it out in a radio transmission, but there's nothing else. This is not rocket science. Somehow, some way, the industry has decided to make this a very complicated thing when it's really not. And if you think about the energy and what you need to control the energy, designing compliant systems is very, very easy to do. So this is a crude representation of what things need to be. So on the left, you see the elements for containing field, two discrete conductors separated by a space. So I've got field sitting here on the left. It doesn't see the space on the right because it doesn't have the rules. Continuous conductors separated by a space. So this conductor is broken, and so the energy here does not see the space. So it's happy over here on the left. It's achieved equilibrium, and it has no reason to move. As the switch starts to close, this field now can see that there's a space to the right that has a different field density or voltage than is on the left. So one of the things that field has to do is to go from a high voltage to a low voltage. That's downhill to field. So that's one of the fundamental things we understand in order to control where it goes so that we know where it goes and it's going where we want it to go. As the switches close, the energy now will move from left to right through this space. And to the energy, this looks like a short circuit because the absolute maximum amount of field that can move in this dielectric based on the dielectric constant, the thickness of the dielectric, and the width of the traces will determine how many coulombs per second or amps can move through this space. So it will be maximized. The other thing, though, it has no idea what's at the other end because it hasn't gotten there yet. So it takes time for it to go from the left side to the right side. It's only 6 inches per, or 150 millimeters per second. It's not moving very fast, even though it's the speed of light. This is one of the things that you have to consider. Once the switch opens, the field on the left now doesn't have any place to go because it's at one voltage, everything's happy. The field on the right will continue to move based on what's at the other end. If it's a closed switch, it will stop moving. If it's a closed switch, it will continue to move into that new space. If the other switch is open, it will stop moving. If it's a load, like a motor or something, it will continue to be converted into kinetic energy until that energy is gone. This is how things work. And this is how you make sure you tell the energy what to do so you know what it's going to do. So the moving field interacts with the molecules both in the boundary materials, the copper in the PC board, and the molecules in the dielectric itself. This interaction causes some conversion of the electromagnetic field into kinetic energy. IR drop is all about how much of the field is interacting with the conductors and with the dielectric. It's quite simple. It's just converted into heat. And the way you reduce the amount of loss is to reduce the impedance and reduce the displacement current that occurs in the surface of the metal structures. So the more compact materials will prevent interactions, and the less compact materials will encourage interactions. So semiconductors just have a way of changing their ability to make that connection between the two wires in the thing. So all of this is about energy moving through the space and interacting to some extent with the materials that are in these transmission lines. So there's energy lost in that conversion to heat as it pushes or bullies around the molecules that are in the dielectric or in the copper. There's also, as you have a changing electric field, it will create a changing magnetic field in the two conductors. That changing magnetic field will cause a changing electric field in the adjacent space. So that changing electric field will find another conductor and cause a changing magnetic field in the next conductor, and then cause a changing electric field in that next dielectric. So you have energy that's leaking at the wavefronts, basically because it's walking through the board. And this is how crosstalk is all about. And it's always going to happen. And the progression is an E field in a space not moving or changing. There's no resulting magnetic field. Once the E field sees a reason to move or change, meaning that there's been a space added, that moving E field at the wavefront will cause a changing H field or magnetic field around the conductor that it's being bounded by. So the whole idea is that we've got this misconception based on electrons and wires and return currents and all this kind of stuff. And it's in the application notes. It's in this guidelines. It's all over the place. It's in your history of your designs. That perspective will almost always cause you to have a failure with today's technologies. Again, with large transistor geometries and slow switching, it's no big deal. But now even our power devices, the GaN FETs, are switching in extremely fast speeds so that there are problems with signal integrity in EMC everywhere you go. So the cost for redesigning is anywhere from tens of thousands to hundreds of thousands of dollars. And it's not in the budget, so you're spending profit. And this is what has to stop. Again, this is not how things work, but this is what has been burned into our brains. And we all have to make a special effort to stop thinking this way. There is no return current that you care for. The energy goes from the space on the left in the space between the two conductors to the load. It's a one-way trip. It doesn't go back. The water doesn't go from the mountain to the lake and back to the mountain again. The energy doesn't go from the energy source to the load and back to the load again. Back to the source. It doesn't work that way. So The idea is there are thousands of good design teams spending their time designing things that they're probably sure will not work. And the bottom line is that if the stockholders in these big companies understood that we were wasting their money, that there would be a big revolt. So to call it $1 billion mistake is really an understatement. It's quite a lot more than that. So I want to end with these concepts that I want you to think about. The fields travel in the space between the conductors, not in the conductors. The switching speed of the transistors determines the frequency of operation, not the clock rate. I don't care what frequency your clock is running. I don't care how often something happens. And what I like to say is, I don't care about how often it hurts. I care about how much it hurts. If I have a nanosecond switching event once a year, it's still a gigahertz signal. And I have to design my system to deliver energy to a gigahertz signal, and I have to design my transmission lines to be able to catch properly a gigahertz wavefront. Signal and power conductions need to be one dielectric from ground from source to destination. You can't separate power and ground. And I don't care what app note or board stack up you get from what company, including mine, if you separate power from ground, you're going to have problems. All signals need to have a goal of the signal conductors need to be one dielectric away from ground. And ground is the continuous conductor that goes from the power supply to the load. Next to that is the continuous dielectric. So two of the three elements are already predefined in your designs. The only thing you have left is to design the switching conductor that goes into and out of ICs and connects these transmission lines. It can be the adjacent plane, which is the best, or if you don't have ground plane, you have to use coplanar ground. An example would be in a 4-layer design. If layer 2 is ground, 1 and 3 are great. They are next to ground. Layer 4 is not next to ground. It is a single layer board. So you have to route it with coplanar grounds. And when you route from 1 or 3 to 4, you need not just the signal tray via, you need a ground via to connect the dielectrics between the horizontal, between the layers, to the coplanar dielectrics on layer 4. I hear things about noisy ground. I saw something on LinkedIn this week about what is the noisy node. There is no noisy node. Noise is a space. There's no such thing as noisy ground because ground is one conductor. It doesn't know what to do because it doesn't control anything. Noise is unwanted changes in voltage in a dielectric. So if there's noise, it's because there's a poor transmission line design. And Dr. Todd Hubing, who's probably one of the best EMC guys, says, thou shalt not split ground. One of the sayings from the signal integrity consulting community is, if they see more than one ground symbol on a schematic, they know there's lots of money to be made because it's really, really difficult to manage and create and manage discrete domains. So one ground to rule them all. Anytime you break any of these rules, you're going to increase system noise and be more likely to fail EMC. So this is the picture you want to burn into your brain instead of that circuit diagram. You just need 3 things to control the energy. 2 discrete conductors separated by a space. You only get 3 components. You get the conductors, the space, and a switch. And then you can only do 3 things with field. You can store it, move it, or convert it to kinetic energy. We're just plumbers with very leaky water pipes. Until the fabricators give us coaxial interconnections on our PC boards, we just have to accept the fact that we're not going to be able to keep all the energy where we want it. We just have to do everything we can in order to make sure that it gets from where it is to where we need it to go with enough fidelity and not crash all the other signals around it. We're designing 3-dimensional spaces for managing electromagnetic field movement. And I'm going to end with Ralph saying, buildings have walls and halls. People travel in the halls, not the walls. Circuits have traces and spaces. Energy and signals travel in the spaces, not the traces. So this is a quick list of the agenda that we're going to go through. I'm not going to go through these details, but these are the subjects in the order at which I'm going to try to teach it. I'm going to do some things that are pretty crazy about high performance network processor, how I approached that design and the philosophy that I used, and then end it with some classes on PCB board stack up and ESD. So with that, I'll turn it over to the team at Azitech.
Thank you very much, and thank you so much for your presentation. Yeah, it's really good.
Yeah.
And yeah, does anyone have any questions?
It's being not a guy who designs the boards, but just for the manufacturing side and that. It's very interesting to see what you've got to say about it. I mean, I don't understand all the technical terms and everything else, but I think it's put in a very plain and sort of understandable way. I've seen it explained a lot more in detail than that. But
yeah, I'll get pretty
I think
deep
that's
into
a really good, really good way of putting it. Yeah,
the idea is
but
that managers need to be able to understand it. So I try to get, I did a 2-page article in PCB Design and Fabrication magazine. This whole thing came out of a request from the IEEE EMC Society for papers, and I sent in a proposal to talk about this perspective, the $1 billion mistake. They said, this isn't scientific enough. We don't want you. And so I went to Mike Buto, who's the publisher of PCB Design magazine, and said, would you like to do this article? And he says, absolutely, we'll publish it. So it ended up being the cover article of the January 2022 magazine. And from that article, I've gotten 0 negative feedback. And the idea was to present these concepts in an understandable way that normal people who aren't physicists, who haven't studied, the calculus, can understand the behaviors. Yeah. Once you understand the behaviors, you can make the right choices in your first circuit board and system design. And the results are incredible. There is no black magic in electronics. The only thing really magic is the actual energy itself. We don't even know what electromagnetic energy is. We don't know how it moves through space. We don't know what magnetics is. We take all this on faith. But we have learned some rules and materials that we can use to control this magic to do things that will do what we want, to do the work we choose. So we believed in the wrong thing being magic. EMC is not black magic. The whole idea of the energy itself is magic, because even at the quantum level, we don't understand all the things that are happening. In fact, my mentor was studying, he said there's things that we're missing, and he was studying quantum mechanics because he knew that there was something that we needed to understand at that level in order to be able to make better choices and design better systems. But he passed away in 2019 without knowing that. So any questions, I'd be glad to honor it. The other thing I wanted to make is that when we do have this seminar, I'm going to make myself available to do board design reviews for the attendees. I do this on a regular basis for my large automotive customers. I have a design review this afternoon for an instrumentation company here in Michigan. I do this all the time, and I try to integrate the training with the analysis. I start with the board stack. I look at your management of power system, power supply. The foundation of every board is the power distribution system. It's the most important net. Clock signals are nothing. Power supply is everything. And that's what we usually screw up. Right. Almost all of the EMC issues, especially radiated emissions that I've dealt with, are direct results of poor PDN design. And it's because we're taught that wrong too. It's time domain based. It's not a network impedance. These impedance targets that are given by the IC vendors are meaningless. What does a 250 milliohm impedance mean to a power supply? Well, to achieve it, you need a 1-inch wide trace and a 1 mil dielectric, which isn't practical, and you don't need that. What is really needed? And I've been working with Murata actually, and they've been doing some simulations with the ANSYS tools to show that it's really time domain. It's how far away from the transistor is that first power source? Where's the first capacitor? And that perspective changes everything. Where I care about low impedance is between the IC and the first bank of capacitors. And I need to have the capacity to deliver that much energy every time the clock fires. but it doesn't need to be all the way back to the PMIC. You know, it takes forever. The PMIC's, you know, milliseconds away. I need to supply energy in picoseconds. So that whole perspective doesn't make any sense. And these are the things, the myths that we were taught and the perspectives we apply to our designs that result in the billion-dollar mistake. So thank you.
Yeah. Sounds very simple when you explain it. Thank you so much.
It is. It is
and I can't
really easy. I don't
can't
care if
wait
I'm working on a network processor or an inverter for an electric vehicle. The rules are the same. AC transmission lines from the power plant. Ralph said all it changes is the geometry. It's all ratiometric. You don't need anything but algebra.
And I hope that that the participants of the actual seminar will also take up this advantageous deal that you're offering with, you know, the face-to-face, where it's a Q&A session with each of them. We'll do that pre to the actual seminar as well, and we can do it afterwards as well. So to round it up, I mean, the actual seminar is taking place on the 18th to 19th of November in Copenhagen. So yeah, well, thank you so much again, Dan, for your time here, and we look forward to seeing you in Copenhagen.
Yep, that's great. And you have the PDF that you can share with the people who've registered, and then maybe post this video on LinkedIn, you know, or on your website at worst.
Yeah,
will do. Thank you so much.
Because the more we can get Ralph's message out, the fewer people who are making billion-dollar mistakes.
Yeah, we are here. We are here to support.
Thanks very much.
Yeah, thank you very much.
Thanks, everyone. Have a great day.
Okay, that's great.
Have a good
good
time.
And you.
Yep.
Goodbye.
Bye bye.
Thanks, Dan. Bye bye.